Okay, so welcome back to our final talk of today. We're following that with a discussion. So our final talk is from Peter Read from the University of Oxford. Peter's an expert in rotating fluids, both in experiment and theory. And today he's going to talk about inhomogeneity and anisotropy in planetary turbulence. So over to you, Peter.
Okay, thanks, Steve. I should first of all, as is customary, thank the organisers and particularly feel very honoured to have been invited to give this talk in this particular context. So my remit, I guess, is going to the opposite end of the spectrum from Béranger's talk that we heard earlier on, which was focusing on the very, very small scales. My interest is somewhat similar and I hope complementary to what we heard from Jeff Vallis earlier in the week concerning large-scale atmospheres and ocean type flows in particular, although I'm hoping to focus on a little bit more on some slightly different aspects of what Jeff discussed, but there will be a certain amount of overlap. In particular, focusing on the fact that turbulence on the large scales is very far from the sort of idealized sort of starting point for many turbulence theories based on an assumption of homogeneous and isotropic motion. So let me see if I can make this work. Yes. So as I say, typically turbulence theories historically have started from assumptions of homogeneity and isotropy, but you don't need to look very far to see that real flows in atmospheres and oceans are neither homogeneous nor isotropic, at least on large scales, and we can illustrate this very, very easily. Here's a nice sort of animation of images from satellites, essentially. So these are actually looking at the in the infrared in the water vapor channel where the atmosphere is not completely transparent. And so white regions are moist regions and dark regions are regions where the air is relatively dry. And what you can see is essentially largely a zonal motion, that is motion going from east to west, particularly at high latitudes. The equator's down the middle, and where you can see the motion is sort of in the opposite direction. But all sorts of other things are going on. There are sort of meanders and waves and so on that we can see that are anything but isotropic by any stretch of the imagination. In the oceans, we've already seen pictures that probably were taken from this state analysis, state estimation of the ocean surface that was shown earlier, where again we can see motions typically on a rather smaller scale than we see in the atmosphere, but combinations of jet flows, sort of jet-like currents, and vortices and waves, but again with a predominant sort of zonal structure, but and certainly nothing like a sort of a uniform homogeneous kind of distribution of motion. So what are the sort of typical sources of anisotropy that are relevant to these sorts of scales? The fact that the Earth is a rotating planet is a very important element. So that tends to lead to Taylor-Proudman constraints, the so-called sort of rotational stiffness that affects motion, particularly in the axial direction, and gives rise to this coherence, the sort of axial coherence of flow that gives you a big difference between vertical variations and horizontal variations of flow. But the topography of the boundaries is also another important source of anisotropy, and in particular on large scales, it's the curvature of the planet itself, the spherical curvature, that is a very important source of anisotropy. And then stratification in the vertical. In general, most atmospheres and oceans are typically on a large scale, essentially stably stratified with denser fluid underlying lighter fluid. And that again gives a vertical and horizontal anisotropy to what happens, and makes life very complicated. And of course, the flow is inhomogeneous mainly because the forcing is inhomogeneous, and atmospheres are typically predominantly forced by radiative and thermodynamic processes. But in the case of the oceans, you also have the effects of the atmosphere acting on the ocean itself through mechanical stresses. So basically what we're trying to do, I mean, perhaps this doesn't really need to be said, but we want to understand and quantify the impacts of these sources of anisotropy and inhomogeneity on the nature of large-scale planetary turbulence, and this is important for understanding how cascades of energy, vorticity, and various other invariants may take place. It'll have implications for predictability and forecasting, a very practical aspect, and also implications for the transport of heat, momentum, and material tracers, which is important for how the climate system works. And it's also being of increasing interest in introducing the need to account for differences in circulation regime that we see between different systems. So certainly between the atmosphere and the oceans on Earth, but these days we can study other planets which have atmospheres or oceans under very different parametric conditions to what we see on Earth. And this is something that I will hopefully have time to get into a little bit later on in the talk. So just before I move on, I just wanted to add this shameless plug for a book that Boris Galperin and I edited that was published actually almost exactly 2 years ago now, that contains a huge compendium of review chapters by a whole range of very distinguished people on this whole topic of particularly the zonal jet aspects of anisotropy in these systems, both in planets and also analogies that we find in magnetohydrodynamics and in plasma physics as well, which I would commend to the House as if anybody's interested in following up some of these aspects in more detail. So just to start from something very simple and familiar, it's very often stated rather glibly that the large-scale turbulence in atmospheres has features in common with rotating or 2D turbulence. So, as I say, the strong rotation can induce this effect that flow becomes coherent along the axis of rotation, and this therefore makes the flow behave as if it were somewhat like a 2D fluid. It's dominated by solenoidal flows, vortical flows, and that changes the conservation properties. It means that quasi-geostrophic flows tend to conserve both energy and entropy, and I'll say a little bit more about what potential means in this context, and what that means is just through arguments based on Furtov's theorem that the kinetic energy will tend to cascade upscale towards larger structures, and also in principle in 3 dimensions towards what we call a barotropic mode, a mode that doesn't vary significantly in the axial direction, while entropy, the squared vorticity, tends to cascade downscale, and hence what we see is flows that tend to start out with lots of small vortices tend to evolve towards flows dominated by much larger vortices. This has been sort of generalized something like 50 years ago now, I guess, by people like Jules Charny and Rick Salmon, into an extension that takes some first account of the density stratification aspects of geophysical flows. So the flow is still essentially dominated by solenoidal components, which are sort of quasi-horizontal in various ways, but in which we can introduce 2 or more vertical degrees of freedom. The fact that density stratification is involved means that energy can be both kinetic and potential, and APE is just short for available potential energy. And also we can then define an extension of vorticity, essentially that is related to the absolute vorticity dotted with the gradient of temperature or potential temperature. That is also then a conserved quantity that serves the same purpose as ordinary vorticity in 2D turbulence. It leads to other modes of instability, particularly so-called baroclinic instability, which essentially leads to the unstably growing Rossby waves that gain kinetic energy at the expense of the background potential energy, and tends to convert APE to kinetic energy at a particular favored length scale, this so-called Rossby radius or deformation radius, indicated here by KD, actually, as shown here. So we have a sort of schematic idea of how the turbulent cascades might work in relation to both baroclinic energy and barotropic energy, with the idea that baroclinic instability converts baroclinic potential energy essentially into kinetic energy at around about this favored scale, this deformation radius scale. Kinetic energy then tends to cascade in the barotropic case towards large scales, while the entropy tends to cascade towards small scales in a similar way to conventional 2D turbulence. And the conventional view is that this is essentially a spectrally local incremental cascading wave number, which I've sort of illustrated schematically here. So as I say, the Fjordhoff theorem and these well-known heuristics lead to these expectations about available potential energy also cascading downscale, while kinetic energy cascades mostly upscale from this deformation radius. And for scales that are smaller than the deformation radius, then the flow is essentially dominated by this entropy cascade, and you get this typical spectrum that has this break between a k to the -5/3 and a k to the -3 at around about the deformation radius.
May I ask a question, please, to clarify things? Okay, because we have like 3-dimensional object, and then you go to the barotropic and baroclinic, and then you would like to compare the barotropic with the 2D turbulence. So can you be more specific when you talk about inverse energy cascade? Which part of the energy? Is it the one in the barotropic mode or the full energy? And when you talk about entropy, are you talking about the entropy in the barotropic mode?
It's the potential. It's the potential entropy which contains contributions from both baroclinic and barotropic contributions, but the inverse cascade is primarily in the barotropic mode, as far as I understand it.
Okay, thank you.
Okay, thanks. So, of course, the acid test with these simple paradigms, of course, is when you confront it with observations. And then there's the famous observations that were obtained by Nastrom and Gage based on observations of wind fluctuations, mainly from commercial aircraft. In fact, they were then able to obtain an estimate of the kinetic energy spectrum actually in the atmosphere, at least at a particular level. And the curious feature here is that of course they saw both a k to the -3 segment and a k to the -5/3 segment, but the wrong way round. So what they find is that the k to the -3 steep spectrum was found at large scales, length scales greater than 700 kilometers or so, whereas the -5/3 spectrum was found at the rather smaller scales, scales smaller than 500 kilometers. Now that's all very well, but what does that actually mean in terms of the actual sense of any turbulent cascades that were taking place? Now the -5/3 segment was speculated initially to be essentially an upscale energy cascade, in which it was supposed that the convective sources would be dominant and actually generating energy at very small scales, at the sort of kilometer scale. But this was in fact not found to be consistent with the third order structure functions that were then calculated by Eric Limborg and his collaborators, who indicated that in fact the sense of energy transport in the atmosphere, at least at these levels, was actually predominantly downscale at these scales, which immediately, of course, raised difficulties for the paradigm that we were dealing with, based on classical quasi-geostrophic turbulence. So, how can we measure turbulent? Just a second, I may have. Yes, sorry. So how can we actually measure turbulent cascades? Now, the structure function is a classical way of doing it, but one can also derive this if you have enough spatial information to be able to do a scale by scale energy budget directly in spectral space, in spatial spectral space. And in planetary atmospheres, it's sensible to use spherical harmonic representation. So we can represent the terms such as the entropy tendency in spherical harmonics with indices n and m, where m is the zonal wave number. You can convert this to an energy interaction term, as shown here, and that can then lead to essentially a spectral flux, which we get essentially by integrating over wave number for both entropy and for the kinetic energy, at least based on the rotational component of the flow using this kind of formalism. This has been recently extended by Pierre Augier and Eric Limborg to give a more complete energy budget that is not limited to geostrophic motion, where we actually look at the rate of change of both a kinetic and potential energy due to various sources, including vertical transport as well as horizontal transport. So we can define the kinetic energy in this way, and the potential energy in this form, based on essentially quadratic quantities in potential temperature. And the various terms on the right hand side involve conversion between potential and kinetic energy. We also have the vertical fluxes that can be represented in this way, and then we have the nonlinear terms, which are the TKLMs. The conversion term is essentially representing the correlation between vertical velocity and density fluctuations, and is represented in this way. And then the spectral fluxes are essentially obtained by integrating or summing over wave number and height in the way that we show here. So for the kinetic energy fluxes, but we also do the cumulative conversion formalism in this way too. And if we apply this directly to turbulence in the Earth's atmosphere, then we can actually analyze outputs from high resolution numerical models, and that's what we show here. So Auger and Lindborg, in fact, analyzed data from two different models. The main model that they're looking at here is a very high resolution Japanese model for the Earth simulator. So it's a triangular truncation up to 600, wave number 639. For various technical reasons. And what we show are the various terms here that actually show how the cascades of energy and entropy were actually working in these models. So the simpler case was looking at the entropy fluxes at different levels, and that actually shows that the entropy fluxes are all predominantly positive, and positive means essentially downscale. So this is showing a result that is essentially consistent with expectations from this classical quasi-geostrophic budget. But the other fluxes, the energy fluxes, behaved in a somewhat more complicated manner, as you can see here. The blue line essentially represents the potential energy flux, and the classical QG theory was predicting that this would be downscaled at all scales, and that's certainly consistent with what we find in the model. But the kinetic energy fluxes are certainly much more complicated. So, and it turns out to be important to separate the vortical component of the flow from the horizontally divergent component. So by performing essentially a Helmholtz decomposition. So what we find is that at the largest scales, essentially at the low wave numbers, the vortical component essentially shows the upscale negative flux, as we can see here with the red dotted line. But the divergent component, which is the sort of the non-geostrophic part of the flow, actually is seen to be a forward cascade at virtually all scales, and actually becomes dominant at the smallest scales. In fact, over the scales that Lindborg and his associates actually deduced from the observations of the atmosphere, which is encouraging. In fact, the conversion term we can also interpret in various ways as well, just to show how complicated the whole problem is. So we see a feature at very low wave numbers, where this green line essentially has a negative gradient, is essentially where potential energy is being converted into kinetic energy. And this is actually at the very lowest wave numbers is a reflection of the large-scale meridional overturning, the zonally symmetric component of the overturning circulation on a planetary scale, whereas we actually get two segments where this conversion is taking place. So there's also another region between wave number sort of roughly 10 and 20 and 30 or so, which is actually representing the effects of baroclinic instability. The other aspect of the inverse energy, kinetic energy cascade is that this is not only sending energy eddy by eddy towards large scales, but is also ending up with putting energy into a zonally symmetric component of the jets. So part of the jet stream that we actually see and hear a lot about in weather forecasts arises as a direct result of this inverse kinetic energy cascade as part of the global circulation. And then we have this curious region at the sort of smaller scales, where the cascade is dominated by this divergent component of the the circulation, mainly in the form of waves, at least in the model. So that's the atmosphere. What about the oceans? Now the oceans are, it's much harder to observe and measure the oceans, but there have been some recent studies that have taken us quite a long way. So one particular study that I would mention is this result on the left by Balwada and his colleagues, who were measuring essentially structure function information from floating probes in the Gulf of Mexico, where they were able to essentially measure and sample the structure function on scales all the way from 10 meters up to nearly 1,000 kilometers. It's quite a considerable achievement to be able to span such a wide range of scales. But interestingly, they also come up with a picture that is surprisingly similar to what we find in the atmosphere, namely that at the smallest scales, the flow is dominated essentially by the divergent component, essentially the green line here on the left, whereas the rotational component becomes dominant at the larger scales, and at scales greater than or similar to the deformation radius, this L sub r, then what we find there is that the third order structure function is also consistent with an upscale cascade at scales larger than the deformation radius, but downscale in a region which is dominated essentially by these divergent flow components. And this was preceded by some direct local measurements that were actually derived in the form of a continuous spectral flux of kinetic energy that more or less bears out the same kind of result. So upscale cascades at scales larger than the deformation radius, and downscale at smaller scales. Another aspect of ocean circulation that has also only fairly recently become apparent, partly from observations and partly from high-resolution numerical modeling, is the aspects of ocean currents that have this very zonal character. So it was found that there are weak ocean currents that can be derived from time averaged data that actually shows the development of these parallel eastward and westward currents, particularly in the mid-latitude Pacific Ocean. And it's the origin of these zonal flows that I think is of considerable interest in terms of understanding sources of anisotropy. So where do these zonal jets come from? And the predominant view now is that this is largely a product of the spherical curvature of a planet. So that imposes an extra, what we call a planetary vorticity gradient. So when we consider the vorticity conservation equation, in the presence of rotation, we can essentially boil the equation down to the conservation of a quantity which we can call the potential vorticity, that includes a contribution from the rotation of the planet itself as projected into the local vertical. So hence we have a planetary vorticity component that is purely a function of latitude, as well as the relative vorticity. This allows the presence of waves. This is essentially what leads to the Rossby wave structure that is shown schematically here. And the important point about these waves is that they are highly dispersive and also very anisotropic in their propagation. So they tend to propagate in the zonal direction, the east-west direction, with a frequency that is highly dependent on wave number. So why zonal flows then? So if the flow is in a range of scales is dominated essentially by Rossby waves, then we need to understand the dynamics of interacting Rossby waves, and these interact primarily in the form of resonant triad interactions. And it was shown comparatively recently by Sasha Balk and his colleagues Sergei Nazarenko and Barbara Quinn, that weakly nonlinear triad interactions of Rossby waves in fact end up conserving 3 invariants instead of the usual 2. So in addition to energy and entropy, they also conserve this other invariant, the so-called zonostrophy density, which was defined here. So under resonant conditions in which the wave numbers satisfy these selection rules, this also leads to essentially a conservation of the zonostrophy density. And the net result of that is to constrain the possible directions of the interactions, and actually then makes this triple cascade act in a very anisotropic way. What it means is that energy essentially has to cascade not just upscale, but it has to cascade upscale, but towards the kx equals 0 direction, rather than simply towards the origin, whereas the zonostrophy density will tend to cascade towards the origin, while entropy tends to cascade away from the origin in this simple way. This was illustrated actually many years ago in a qualitative sense, including by Jeff Vallis, among others, in which we could see decaying turbulence that started out with a energy concentrated just in a ring of constant magnitude wave number in wave number space, as we can see here in the lower row. And as the flow evolved, we could see energy essentially moving inwards, but ultimately collecting towards the ky axis in this sense, and the corresponding flow in real space, of course, was then developing this highly zonally elongated kind of structure. So we end up having to modify our quasi-geostrophic turbulence paradigm in various ways. So notably, one thing that we also find with wave-dominated flow is that not only can you get energetic interactions between nearby wave numbers, but with triads you can also get interactions directly from high wave numbers directly into zonally symmetric structures, and in fact the simultaneous conservation of these 3 invariants in fact makes the interactions with the zonal flow component become the most favored form of interaction. So this you could regard not necessarily as a cascade, but more like a waterfall, a direct transport from high to low wave number over large distances in wave number. So finally, that in terms of conceptual models, an extreme form of this zonal type of cascade leads to what has been termed this zonostrophic regime. So this is a particular situation where friction and forcing is relatively weak, and the forcing is primarily taking place at relatively small scales, at high wave numbers, indicated here by NZ. And this initially will lead to an isotropic inverse kinetic energy cascade, at least in the barotropic mode, until it reaches this transitional wave number was first identified by Pelinovsky in the 70s, which corresponds to where the period, the Rossby wave period, is approximately equal to the advective time scale, and is given by this beta cubed over the cascade rate, the energy transfer rate, to the 1/5. And for larger scales, then essentially the flow is dominated by these weakly nonlinear Rossby waves, and the cascade becomes highly anisotropic, and in particular pumps energy into the zonal flow, so that what we end up with is a very anisotropic energy spectrum, in which if you separate the zonal flow from the rest of the flow, the non-axisymmetric flow, you see the non-axisymmetric flow obeys the usual Kolmogorov spectrum for an inverse energy cascade, whereas the zonal flow tends to adopt this much steeper spectrum with a limiting slope of around about -5, and is in fact seems to be a universal spectrum that's only determined essentially by the rotation of the planet, and not by any other aspect of how the flow is forced. So as an intermediate conclusion, then what we see is that we have this quasi-geostrophic turbulence paradigm. Although it's quite old, it's still quite useful as a schematic representation, provided you modify it to include the effect of zonal flows by these spectrally non-local wave zonal flow interactions, at least for the barotropic components of the flow. Also at small scales, we need to allow for the possibility of the horizontally divergent component of the flow becoming much more significant, and raising questions as to what is the role of these of dispersive inertia gravity waves in this region, as compared to more direct stratified turbulence, which of course raises interesting questions as to how well these models can represent this sort of behavior, because to represent fully developed stratified turbulence would probably require much higher vertical resolution, particularly than is customary in atmospheric models. We've spoken almost entirely about the Earth, but what about applications beyond the Earth? As I mentioned before, there are solar system planetary atmospheres, atmospheres of other planets that are in rather different parameter settings to what we're used to seeing on Earth. So we can sort of compare these planets by using various dimensionless numbers. It's conventional to use, for example, this quantity known as the thermal Rossby number, which is essentially a ratio of forces between inertial forces and Coriolis forces, in a sense, or the so-called Berger number, which is essentially a ratio of length scales, a ratio of the deformation radius to the radius of the planet, indicated here by A. We usually show these as the squared ratios. So if we consider, for example, the atmosphere of Mars, so Mars is a rocky planet rather like the Earth, has a thin atmosphere of carbon dioxide. The planet itself is roughly half the radius of Earth, but rotates at almost exactly the same rate, presumably by coincidence. Recently, Mars has been the subject of a huge number of space missions to actually measure its environment in considerable detail. And it's now possible to, because of orbiting weather satellites around Mars itself, we can actually perform state estimation reconstructions of the atmosphere and its circulation directly by combining with numerical simulation models in much the same way as has been done for the Earth's atmosphere and oceans. And so what I show here are some preliminary results from analyzing climate results over 3 Mars years using a general circulation model that was developed jointly between my own group and groups in France and Spain. So this shows the example of the spectra, the energy spectra that we actually observe in this state estimation in a time average sense. And we can see these are actually compensated spectra. So horizontal lines are essentially indicating k to the minus 5/3 spectral slopes, whereas and we also indicate the k to the minus 5 and k to the minus 3 with these other lines, so that we can see that at higher wave numbers, at smaller scales, there is a tendency for the potential energy to follow a k to the minus 5/3, so that though the kinetic energy still has a slightly steeper slope, but we see that the zonal kinetic energy component does seem to have this k to the minus 5 sort of tendency, at least at large scales. We can not only look at the spectra themselves, but we can also derive the spectral fluxes, given that we can reconstruct the entire circulation. And what we can see here is evidence here of similar tendencies to what we see in the diagnostics for the Earth. So we see the potential energy, the blue curve is essentially showing a forward flux at all scales, whereas the kinetic energy has a flux that changes sign. And if we decompose it again into rotational and divergent components, then we can see that the rotational component has a very weak region of upscale transfer. Again, upscale of the deformation radius scale, which is indicated by ND here. Whereas at smaller scales, at higher wave number, then we see that the divergent component essentially dominates. In fact, it tends to dominate at most scales. Sorry, let me go back. The divergent component essentially dominates at all scales in the Mars case, and is downscale at all scales. But we can see evidence of baroclinic conversion from potential energy to kinetic energy, both at the very low wave numbers, which are associated again with a meridional overturning in a zonally average sense. So that's what this segment of the conversion term refers to. But then we also have this region here also with a negative gradient with respect to wave number that is associated with baroclinic instability in much the same way as we see on the Earth. This is in contrast to the atmosphere of Venus. So Venus is sometimes referred to as the Earth's evil twin, mainly because it has surface conditions that are rather hell-like. It has a very high pressure carbon dioxide atmosphere with very, very high temperatures at the surface. But Venus is a much more slowly rotating planet than the Earth. It's almost the same size as Earth, but has a basic rotation period that's 240 times slower than that of the Earth. But it nonetheless has very strong winds, and that's what's indicated in the bottom left here. The colors essentially represent the east-west wind with this strong prograde zonal jet at fairly high altitude. And the contours essentially are stream function contours of the meridional overturning. So we see that there are essentially planetary scale overturning motions, and that is essentially how the circulation can be idealized. So we are here using a high resolution numerical model built on the same with the same components essentially as for the Earth and for Mars, but with realistic radiative forcing and so on at a spatial resolution of 1 degree or so. This shows again that we see energy spectra that are actually similar in some respects to what we saw on Earth, but with some significant differences. So now we see a k to the minus 5/3 in both kinetic and potential energy, and this extends essentially over almost all scales that are resolved, except at the high wave number n, which is probably a model artifact. But we see that the zonal flow this time doesn't follow a k to the minus 5, it follows something more like a -3. So this is typical of an atmosphere that is very much out of the geostrophic rapid rotating regime. And the spectral fluxes are correspondingly also somewhat different. So we still see potential energy fluxes essentially downscale. In fact, we see almost all fluxes to be essentially downscale, right away from the planetary scale downwards. But this time, the rotational component of the circulation plays very little role at all. Almost everything is essentially determined by divergent components. All we see in the conversion term is a signature which is associated with the meridional overturning. Well, moving on to at the other end of parameter space, we can look at the gas giant planets. So these are now again getting very well observed by various spacecraft. And not just spacecraft, but also even ground-based telescopes these days can do an amazing job of imaging the clouds on these planets. So Jupiter is a very rapidly rotating planet. It rotates something like twice the rotation speed of Earth, but is 10 times the linear radius. So these are absolutely huge planets, Jupiter and Saturn. And we see here images both in the visible showing the clouds of mostly ammonia ice, and on the right hand here we see an infrared image which actually shows it's almost the negative of the visible image on the left, because what we're looking at here is thermal emission from regions below the clouds. We're looking at holes in the clouds essentially. So the particular peculiarity of Jupiter and Saturn is the flow that is very much, extremely anisotropic. So we see the flow is organized into these, the clouds are organized into zonal bands, and the bands are essentially organized themselves by this pattern of eastward and westward zonal jets. This shows the velocity as a function of latitude from tracking various cloud features. And we see these jets have all sorts of interesting properties. They seem to violate the classical stability conditions for Rayleigh stability of zonal jets, and they also are can be demonstrated to be maintained essentially by momentum fluxes, by direct interactions between eddies and the zonal flow at a rate which is surprisingly high, something of the order of 10 to the minus 4 watts per kilogram at the cloud level. So it's now possible to analyze the winds that we can measure at the cloud tops from these structures. We can obtain fully two-dimensional wind fields over most of the planet, particularly from the flyby of the Cassini spacecraft in 2000, and this made it possible then to actually generate kinetic energy spectra essentially for Jupiter's atmosphere, and we're also doing it now for Saturn's atmosphere, which I show here. And this actually shows a clear evidence of the k to the minus 5 kind of spectrum of the zonal of the purely zonal flow, but the spectrum for the eddy field is actually rather more complicated, but there is some evidence of a k to the -5/3 segment actually on both Jupiter and Saturn. But what about the direction of the energy cascades on Jupiter? Well, given the winds that we have, even though we only had essentially 4 snapshots of the wind structure, we could still do a spatial average of the spectral fluxes, and we're able to deduce the following here for both the entropy and the kinetic energy flux at the cloud tops of Jupiter, which clearly show a forward cascade for entropy for entropy, whereas the kinetic energy flux was much more complicated, and actually shows this evidence of this sort of multiple cascades essentially. So with the presence of an inverse cascade over a range of scales, a forward cascade at the smallest scales that we could resolve. Interestingly, with a turnover that's very close to a length scale that is comparable to what we can deduce to be the deformation radius, and then a convergence of kinetic energy at a scale which corresponds to the zonal jets themselves. In fact, a further decomposition actually shows that this inverse cascade particularly is dominated by direct interactions between eddies and zonal flows rather than by any sort of incremental cascade, almost by a factor of 10. Yes, so the fact that we see this kinetic energy source essentially at this particular length scale is suggestive of a role for baroclinic instability in Jupiter's atmosphere, much as we find in these other planets, Mars and the Earth itself. So more recently, we've had the Juno mission, which is now looking at some of the vertical structure of these flows. We see that the zonal flows are in fact significantly baroclinic in their structure. They're not height independent in quite the way that you might expect, just purely from an application of Taylor-Proudman. And this is almost certainly because of temperature and composition variations with depth. So there's all sorts of sort of complications that are being revealed by these measurements. So the microwave measurements from the Juno spacecraft allows us to go sort of several hundred kilometers down, but that's still relatively shallow compared to the radius of the planet itself. We can also look at the structures of some of the other sort of more localized features. So the Great Red Spot, for example, this oval anticyclonic storm that's been observed for hundreds of years, turns out also has complicated structure in the vertical, but is actually surprisingly shallow. It seems to be probably no more than about 500 kilometers or so deep, compared to the zonal jets themselves that have been deduced to penetrate something like 3,000 kilometers into the planet from the visible surface. But there are various other features that are quite intriguing and far from being well understood. Jupiter and Saturn are thought to be fluid planets throughout because they're mainly composed of hydrogen and helium. And if you compress hydrogen and helium strongly enough, of course, it becomes electrically conducting. So at some point, magnetohydrodynamic effects will become very important. But curiously, the zonal flows themselves don't seem to penetrate all the way down to the region where we expect the atmosphere to become electrically conducting. So there are still aspects of the vertical structure of the zonal flows that were deduced essentially from magnetic and gravity field measurements that are still yet to be explained, and must presumably also have a strong bearing on what the circulation is doing at these sorts of depths. So just to draw things to a conclusion, so what I hope I've sort of managed to convey is that we can still apply the sort of semi-classical concept of quasi-geostrophic turbulence as a heuristic approach for characterizing large-scale flows in fast-rotating planets, provided we include these extensions for planetary vorticity gradients and the non-local wave zonal flow interactions. But there's still a lot of questions that and challenges that, about what essentially happens between the sort of deformation radius scales and the very small scales, is essentially the Osmedov scale as the ultimate limit beyond which you expect the flow essentially to develop into direct, fully three-dimensional turbulence. So there's still an ongoing debate as to whether this range of length scales is dominated either by divergent gravity waves, with buoyancy forcing as the main restoring force, or fully developed stratified turbulence. So this is certainly an area that needs a lot more effort. Is this range adequately represented in numerical atmospheric models? Almost certainly not. One has to. I'm surprised nobody's already quoted this famous quote by George Box about all models being wrong, but some are useful. I mean, it certainly shows an energy, an entropy cascade that behaves in a reasonably sensible fashion, but whether it's doing it for the right reason, I think, is still a matter of debate. There's also, of course, the question of as to what happens, what role does convection play in terms of inducing cascades within this range of scales, and this, I think, is still quite an open question that still is not well understood. So we have this this kind of revised geostrophic turbulence concept that I think is still a useful idealization. What about slowly rotating sort of non-geostrophic planets? So there we certainly need an alternative paradigm, but which is perhaps related to the sort of the mesoscale part of the quasi-geostrophic turbulence paradigm. But it's interesting then to think in terms of how the properties scale with various parameters, particularly with things like the thermal Rossby number. So we have to have. So in terms of the large-scale gas giant planets, so there are all sorts of interesting questions here that I think are going to present us with all sorts of novel challenges. So the roles of thermodynamic and convective forcing and magnetohydrodynamics all seem to play a role at deeper levels, and trying to unravel this based on the limited information that we can actually deduce from observations is a real challenge. How and where are the jets dissipated, and how do they equilibrate? So the all physical atmospheres are essentially forced and dissipative systems, but where the jets and eddies are dissipated in a planet that essentially has no solid surface is a very interesting question that has both physical and philosophical elements to it, I guess. Is this due to large scale or small scale damping? Well, the jets have to equilibrate somehow or other so there must be some energy sink at large scales as well as the sort of traditional dissipation that takes place on the smallest scales. And one can speculate about deep MHD effects, essentially, and radiative effects and the effects of breaking gravity waves and so on. Another interesting question is, are emergent jet structures the result of some sort of self-organized criticality? We can see that flows, the jet flows actually do seem to stray not very far from a state of almost neutral stability. So is this an accident? And if so, what is the appropriate stability criterion? Is this indeed a useful concept? And if not, then what else should we should we use in principle that might help us to understand what is leading to the equilibrated structure of the jets that we actually observe. And another big question is the origin of large-scale oval vortices. I mean, is this some sort of flux loop sort of behavior where the jets themselves are driven by eddies, and then the eddies themselves become unstable, weakly unstable, and start generating secondary structures? And finally, there is a big need, I think, for, I mean, all the diagnostics that I've actually spoken about are focused essentially on the isotropic, horizontally isotropic component of the flow, but we need diagnostics that also focus on the anisotropic aspects in particular. And so there are certainly a strong need for more diagnostics that can give us good insights into how these anisotropies develop. So I think that is a good point to stop, and I would thank you for your attention.
Thank you, Peter. That was a great talk. We have time for questions, and we have